Cauchy's nth root test. If sum of un can be a series of the terms such that from and after some particular term u to the n to the power of 1 by n, limit between n tends to infinity, is L, then sum of un converges if L is less than 1, sum of un diverges if L is greater than 1, and the test fails if L is equal to 1. So this is an example. Between 1 and infinity, the sum of 1 plus 1 by n to the power of minus n squared. Okay, so here's the formula written over here, and you want to plug this function un into the formula. So this n squared cancels with n to make minus n. Okay, and that can be rewritten as 1 over this, and this is can be rewritten as e. So 1 divided by e is less than 1. Check out the video of proving e. By Cauchy's nth root test, the series converges. So when it is less than 1, it converges, and e is equal to 2.738. So 1 divided by 2.738 is going to be less than 1. So sum of n divided by n plus 1 all to the power of n squared. So this is the whole function. You need to plug this into the formula here. N squared divided by n is n. Take out the common of n and divide it and cancel it down, and you get this. This can be rewritten as 1 divided by e, which is less than 1. So by Cauchy's nth root test, the series converges. So sum between 1 and infinity, n to the power of n squared divided by n plus 1 to the power of n squared. Here un is going to be this function here, which can be written as the whole inside bracket to the power of n squared. And you take this un and plug it into the formula. So n squared divided by n is n. So you can take out the n common, cancel it down, and this is 1 divided by e, which is less than 1. So it converges. Next question. So this one is going to be n plus 1 to the power of n plus 1 divided by n to the n plus 1. So how can you check this? For the first one is going to be 2 to the power of 2. 1 divided by 1 to the power of 1 plus 1, which is 2. So 1 squared. Minus 1 plus 1 is 2, and 1 to the power of minus 1. Okay. Then the second one, 2 plus 1 is 3. 2 plus 1 is 3. 2 to the power of 2 plus 1 3, minus 2 plus 1 is 3 divided by 2 to the power of minus 2. So this carries on in a sequence. Okay, so this is the formula for Cauchy's test, nth root test. Un to the power of 1 by n. So you divide this by n, so you're going to get minus 1. So removing the common factor of n plus 1 divided by n to the minus 1 out, removing this out for these two, n plus 1 minus 1 is n. So you get this n, and this thing is to the power of 1. So 1 minus 1 is 0. So 1 to the 0 is 1, so minus 1. So this can be evaluated as e, so e minus 1, and here is the power minus 1, so minus 1, and this can be evaluated as, you can take out the factor of n, cancel it down, and you get 1. So e minus 1 to the minus 1 is 1 divided by e to the minus 1, which is less than 1. So by the Cauchy's end root test, sum of un converges. Sum of nx divided by n plus 1 to the n. Now this whole thing is going to be un. So using this formula, n divided by n is 1, and you have this here. Taking out n as a common factor, can reduce it down to x. The sum of un converges if x is less than 1 and diverges if x is greater than 1. So next question. So here is going to be n divided by n plus 1. So check. It will be 1, 2 and 3 for n, and 1 plus 1, which is 2, 2 plus 1 is 3, 3 plus 1 is 4, etc. And that would be n squared. So that would be 1 squared, which is 1, 2 squared, which is 4, 3 squared, which is 9, and x to the n, 1, 2, 3, etc. Okay, so that's going to be the un function. You have to substitute this into the formula. Now 2n squared divided by n is simply n. And you can take out a factor of n and rewrite it as this, and this can be rewritten as e. So multiply by x by 1, which is x. So series converges if x by e is less than 1, the x is less than e. Series diverges if x divided by e is greater than 1. For example, x is greater than e. Next question. Sum of n plus 1 to the n, x to the n, x n to the n plus 1. Here we have n divided by n, which is 1, and here x to the n would simply be evaluated as x. Okay, so you want to cancel down this function here and subtract, raise n plus 1, multiply n plus 1 by 1 divided by n, so divided by n, which is 1 plus 1 by n here. So you can rewrite that as n times n root n, and here this can be rewritten as this, and n divides by 1 here, n divides 1 by n, and this can be rewritten as a third. So this simply becomes x. So the given series converges if x is less than 1 and diverges if x is greater than 1. So what happens if x is equal to 1? So you choose the comparison test. So you have un here, you have vn. So for vn is going to be the 1 divided by n, the denominator which is 1, the numerator which is 0. So 1 minus 0, which is 1. You use the comparison test, un divided by vn. You're going to get this, which is e, multiplied by finite and not equal to 0. un and vn and un behave alike. So as sum of 1 by n diverges, hence sum of un diverges. So this is going to be 2 squared divided by 1 squared. So that's going to be n plus 1 divided by to the power of n plus 1 divided by n to the n plus 1 minus that. So this is the un function here, un to the 1 by n, which is minus 1, taking out a factor of this, taking out a common factor of n, dividing by n, here evaluating this, dividing by n and evaluating this as e. You have this as well. You're going to get this 1 divided by e minus 1 is less than 1. So sum of un converges. So sum between infinity and 1, 2 plus 1 by root n to the minus n. So what do you want to do? You want to divide this by n, which is minus 1. So as n tends to infinity, this becomes into 0. So this becomes half, so which is less than 1, so it converges. Similar here, n divided by n, which is 1, take out the n from here, divide, get a third, which is less than 1, so it converges. Here, applying the same steps as before, minus n divided by n, which is minus 1, divided by infinity, which is 0, so 1 divided by 1, which is 1, so test fails. So if L is 1, then the test fails. L is greater than 1, it diverges. L is less than 1, it converges. Next question. Sum between infinity and 1, n squared divided by e to the n. So un is going to be this here. And using the formula for Cauchys nth rule, you're going to divide n squared by n. So you get n. Sorry, you get 2 divided by n. And e is to the power of n, so this cancels down to 1. So e. So this can be rewritten as this squared. And you want to rewrite this as the multiples of these two. The multiples of these two equals to this, which is 1 by e, which is less than 1, so it converges. Next is the integral test. Let f of x be a non-negative monotonically decreasing integral function on between from 1 and infinity. These are the two limits. So it ends here, it starts here and it ends here. Then the series sum of f of n and the improper integral sum between 1 and infinity f of x dx converges or diverges together, i.e. series sum of f of n converges or diverges accordingly. And sum between infinity and 1 f of x dx tends to a definite limit or infinity. So simply they are saying here that the two limits are infinity here and 1 here. So it could converge or diverge, etc. We have to check the convergence of this for this example. For n is, remember, between 2 and infinity, f of n is greater than 0, monotonically decreasing, where n is greater than or equal to 2. Next example, f of n is 1 divided by n root of n squared minus 1 for n is a member between 2 and infinity. Here f of n is greater than 0, So if you plug in 2 here, it's going to be greater than 0. If you plug in infinity, it's going to be greater than 0. Okay, so this function can be evaluated as sec inverse of x. So here's the same thing. So integral of 1 divided by x, root of x squared minus 1 dx. So use the substitution of u is equal to square root of x squared minus 1 to find du by dx, which is going to be 1 divided by square root of x squared minus 1, and find the derivative of this whole thing, which is going to be a half times x squared minus 1 half square root of x squared minus 1, which is a half multiplied by x squared minus 1 to the half minus 1 multiplied by the derivative of x squared minus 1, which is going to be a half x squared minus 1 to the minus half, which is rewritten as 1 divided by x squared minus 1 to the half, which is written by 1 over 2 times root of x squared minus 1, and here is multiplied by this is the chain rule. So you're going to have 2x and 0, so the 2's cancel out, so you get x divided by x squared root of x squared minus 1. So here you're going to get x divided by the root of x squared minus 1. So you want to rearrange for dx, which is going to be root of x squared minus 1 by x du, and plugging in the value of u, you're going to get this thing here. Now for this step you're going to have integral of 1 over, it's going to, so this thing here, this function here is going to be u, is going to be u over here, and that's going to be x. Okay, so x, which is here, and that's going to be multiplied by dx. Now dx can be substituted from here. Okay, so the top function is going to be u again, the top function is u, and the bottom function and the bottom thing is going to be x, right? So these two u's, they cancel out, and you're left with 1 divided by x squared. So x squared can be rewritten as u squared. So taking squares of both sides, you get u squared is x squared minus 1. You get u squared plus 1, which is x squared. And taking the square root of both sides, you're going to get x is the square root of u squared plus 1. Okay, this is a u. So you get 1 over x squared, which is 1 over u squared plus 1, which is here. Okay, and this is a standard integral, which is arctan of u. So 1 divided by 1 plus u squared is the arctan of u, and use the substitution of u from here, x squared, root of x squared minus 1 into here. So you get arctan of square root of x squared minus 1, and this is your final answer. And you can simplify that. You can simplify this arctan of root of x squared minus 1 as minus arcsine of 1 over modulus of x. And that is given here by sec inverse x between infinity and 2. So when that is infinity, you get pi over 2 and minus sec inverse of 2, which is finite. So by Cauchy's integral test, the series is convergent. So using integral test, check the convergence of the series 1 by n squared plus 1, the summation. Here f of x is that, and f of x is greater than 0 and is monotonically decreasing. So as x increases, the denominator increases, and as the denominator increases, the whole fraction decreases. So that's why it is monotonically decreasing. And here you write the un, and this is the standard integral of arctan of x between the two limits infinity and 1, and you get this pi over 2 minus pi over 4, which is pi over 4. So by Cauchy's integral test, it is convergent. So examine the convergence of the integral 1 divided by n log n, summation between infinity and n is 2. So this video is covered in Leibniz test. I will just write down the name. So you can find this video over here in Leibniz test, where Miss covers up this question and the next topic. Okay, thank you for watching.